a capacitor is another type of energy storage device. It consists of two parallel plates that are separated by some dielectric material, some insulator. So what that means is that there's no true direct connection between the plates of that capacitor. But what happens is you end up with charge built up on one plate, positive charge on one plate, negative charge on the other plate, and so you end up with an electric field between those charges. They want to come together. They have a electrical attraction between them, but this insulating material keeps them from being able to come together. And so you have energy stored in that attraction between the charges. If you connected the capacitor to a resistor, for example, the positive charges would flow through that resistor to get to the negative charges, and you could dissipate that capacitor. You could get that energy stored, that stored energy back. And so the way that you get the charge built up on the plates is you have what's called a displacement current. It's a displacement current because the current technically isn't flowing all the way through the capacitor, but you have positive charges flowing in and building up on one plate. You have positive charges flowing out the other side into the rest of the circuit. As the positive charges flow away, you have negative charges that are left. And so from the circuit's perspective, a displacement current through a capacitor or a true conductive current of actual continuous flow of charges are indistinguishable from one another. So despite this sort of quirk, we're going to treat the current as if it flows through the capacitor, and we're going to treat that current the same as any other current. If we have a separation of charges here, we're going to have a voltage across the capacitor. The positive charges are at a higher potential, higher voltage. Negative charges are at a lower potential. And a capacitor is defined in terms of its capacitance. The charge on the capacitor plates, that's these guys here, is equal to the capacitance of the capacitor times the voltage across the capacitor. So the more charge you have built up on those capacitor plates, the more voltage you're going to have, but that proportion depends on the capacitance, which has to do with the physical characteristics. How big are the plates? How far apart are they? What kind of insulator do you have in the middle, etc. So the capacitance is a fixed value for the capacitor. The charge is changing because of the current. The current is the rate of change of charge, how fast charge is passing through, and so if we combine the relationship between charge and current and the relationship between charge and voltage, we end up with this relationship here for our two-terminal element. We have a relationship between the current and voltage for a capacitor. Note that if a current is flowing to the capacitor, that means the current is coming in. That current is bringing charges in. Those charges are building up on the capacitor plates. So if the current is coming in as positive, then the change in voltage would be positive because that increase in charge would increase the voltage. If the current was flowing the opposite way, that would be corresponding to the voltage decreasing, because if current was leaving, that would mean that the charge was dissipating across that capacitor, and so it would be losing charge. So again, be careful of the polarity that we have here. This equation assumes passive sign convention here, where the current is flowing into the positive terminal of the capacitor, and then if the current is going in an opposite direction, or if the voltage is decreasing, the negative sign that would come from that would take care of itself mathematically for us. Also notice that if the voltage is constant, that means that if the voltage is constant, there can't be any more charge going to or leaving the plates, and so if there's no charge moving, then there can't be any current, and thus for a constant voltage, the capacitor acts like an open circuit. It acts like there's no connection, because again, there technically is no connection there. We can do something similar to what we did for inductors. We have a relationship between the current and the voltage, so if we know the capacitor voltage as a function of time, we could figure out what the current flowing to that capacitor would have to be. But if we want to go the other way, if we know the current going to the capacitor and we wanted to find the voltage, what we'd have to do there would be to get the voltage by itself, which would include multiplying both sides by dt and dividing over the capacitance. And so the little change in voltage would depend on a current flowing for a little bit of time. If the current's flowing for a little bit of time, there's a little bit of charge going to that capacitor. That little bit of charge is going to give us a change in the voltage across the capacitor as a result. What else we're going to do is use our scripted variables again, our scripted v and our scripted t as our variables of integration, and we're going to integrate to some function of some arbitrary time t and some capacitor voltage, so that we can find that capacitor voltage as a function of time. So we'll take this relationship here. This is again, each instant that the current is flowing, it's delivering charge to the capacitor, and so the voltage of that capacitor is going up because of that increase in charge. We have to know the capacitor voltage at some point in time t as our starting point, and then knowing the current at every later point tells us how much the voltage is changing from that initial point, and we can use that to figure out what the voltage must be at any later point in time. If we want to solve for V, we'd have to integrate dV to find V. We're going to integrate from the starting voltage to some unknown arbitrary voltage. This is going to be our function of time. And then if we're integrating the other side, our variable of integration here is time t. So we have to integrate from the time that corresponds to that known initial value up to some arbitrary time t so that we can have our a function of time here. We're leaving IC as in general terms because it's going to be some function of time. And so this again is showing us how the voltage is changing. And this is our starting point, so if we know what the voltage was at some point, we figure out how much the voltage changes in this time period. It tells us what the capacitor voltage is going to be later. And by picking some arbitrary variable t, we're getting our function in terms of that same variable t, and so we have our capacitor voltage as a function of time, and not just for a specific value. The power absorbed by any element is the voltage times the current. For a capacitor, the power absorbed by a capacitor is the capacitor voltage times the capacitor current. We can express this as a voltage times a current, or we can express it as a current times a voltage, depending on what information we know and what we're trying to find. Again, this is the energy absorbed by this capacitor, but again, the idea is that the capacitor has absorbed that energy from the circuit, so the energy has left the circuit and gone into the capacitor, into the electric field inside that capacitor. But the energy isn't gone, it hasn't been converted to a wholly different form like a resistor does. Instead, that energy is stored inside the capacitor, and if you reduce the power in the rest of the circuit, for example, the capacitor will release this energy back into the circuit. It will return the energy to the circuit. So the energy is just stored, but it hasn't disappeared. We found an expression for the power being absorbed by the capacitor, but recall again that power is the rate of change of energy. So if power is being delivered to the capacitor, then the energy stored in the capacitor is changing with time. And so if we want to figure out how much energy is stored in that capacitor, what we'll have to do is multiply by dt. So the power delivered to the capacitor times dt is the time rate of change of the capacitor energy times dt. Those two guys cancel. And the power delivered to the capacitor is this function here, which is our voltage times our current, based on our fundamental equations for a capacitor. And again, the t's cancel. And so we end up with a relationship here. For every little piece of charge that we add to the capacitor, then we're going to increase the voltage across that capacitor a little bit, and then there'll be a corresponding increase in the energy stored in the capacitor as a result. We will again switch over to dummy variables. If we want to know the total energy, we'll have to integrate the total energy, and then we'll integrate the voltage, and we'll see how each little change in the voltage increases the total energy, and we'll find that relationship. In this case, our starting point, or our reference point, is to say that zero voltage, zero charge built up on that capacitor would mean there'd be zero electric field stored in the capacitor, and so there'd be zero stored energy there. So we're starting from zero, and we're looking at, for each little bit that the voltage goes up, how much does the energy go up? And we end up with this relationship here, and then again I've written it kind of in long form to reinforce the fact that the voltage is a function of time, and so the energy stored in the capacitor is also a function of time. But remember this relationship there.